we're very excited to have with us today John Wilson from Siemens. So John is part of the Siemens Digital Industries software business unit with Siemens. He has an immense amount of experience when it comes to electronics and thermal design consulting. As you can see, 20 plus years of experience in the industry and field, and has managed over 100 electronic thermal design consulting projects. And he will really be leading and doing the majority of the presentation for us today. We're excited to have him share his experience and knowledge with us. In addition, my name is Daniel Mazar. I am the host of this presentation and this webinar series. I'm part of Maya HDT, and I'll just be introducing the organization in just a moment. Great. Moving on. As I mentioned, Maya HDT is the one hosting this webinar. We are a leading provider of digital engineering solutions and the top gold partner for Siemens Digital Industries software. Maya has a strong history in aerospace, but has been working with multiple industries to help solve complex engineering challenges over the past 3 decades. We've seen immense growth around the challenges and adoption related to electrification and electronics cooling. And we have clients working on these types of cutting edge problems all over the world, and we support them from our offices in the US, UK, and Canada. So today we're covering a small subset of our expertise. And as I mentioned, it's going to be focused on simulation, a little bit in design, but mostly in electronics cooling. But there's a lot more to the table that we're not covering today, but we can cover in the future as needed. For example, if you're looking at putting a holistic digital thread in between your entire engineering workflow, and you want to look at comprehensive digitalization or having a digital twin, these are areas where we can definitely provide some assistance. In addition, if you're looking at some form of real-time monitoring, implementing IoT or AI-related strategies, we do have strong expertise in these areas as well. We won't be touching on those today, but if you'd like to have a follow-up conversation, please don't hesitate to send us a note on that as well. Now, before passing it on, just one last point I wanted to mention, which was on what we're doing today. So we had our first session last week where we spoke about the fundamentals of electronics cooling. Today we'll do a deeper dive on the thermal performance of IC packages. John's going to be showing us hands-on some very exciting things in relation to this. And again, this is going to be the second part of a 4-part series. So with that, John, I'll pass it over to you, and I'll be on standby if you need anything. Take it away.
Great, thanks, Dan. Okay, this is we'll start. This is the entire Simulate series, and like Dan mentioned, today we're going to talk about the thermal performance of IC packages. There's kind of 3 major themes here. Really, is why is it important, and how are IC packages modeled? There's different ways to model them, and part of that reason is computational expense. You may make that choice based on where you are in the design process. So we'll look at different ways you can model IC packages. And then lastly, how are IC packages calibrated? How can you kind of verify or validate the accuracy of the modeling approach? Oops. So why is it important? You know, when we do thermal design, most of it is we look at what is the junction temperature of our IC devices. That kind of drives a lot of thermal design and electronics. And the reason we do that is really because temperature is a good lead indicator of field reliability. It may not always be the reason for failure, but it does give us an indication how reliable our design will be based on the temperatures that we're getting for the IC devices. Most failure mechanisms increase with temperature, just the steady state operating temperature of the IC devices, but they are also influenced by temperature gradients in space. You know, materials in the IC package have different coefficients of thermal expansion. So as devices heat up and the temperature there's a gradients within that package, you get different materials expanding at different amounts, and you could get cracks or delamination at where these materials are bonded together. So in solder joints or where materials are glued together. So that could happen, that could affect reliability. We also look at rate of change with time, just the cycles, temperature cycles the part is exhibited to during its lifetime, and that's influence on reliability. So if we can actually just reduce the steady state operating temperature, it's going to affect and reduce the temperature gradients within that package, and also the temperature cycles, the amount of delta in each cycle, because we just have a lower steady state operating temperature. I do want to point out that we do offer hardware to measure the cycles of a part. So we have the power tester here where we can cycle that part, and we can measure the thermal performance degradation of that part as a result of temperature cycling or power cycling. And also, when the part fails, what component within the IC package failed. And this is a typical plot you would see, as the larger temperature swings in the cycle is going to reduce the well, the larger the temperature cycle, the more the fewer cycles to failure. So if we increase the temperature change for our cycles, it's going to have reduced lifetime. And this would be an example of low cycle fatigue, and most electronics wear out due to low cycle fatigue. So while we generally look at, when we do a thermal design, like I said, it's junction temperature. It's most of the time it's all about the junction temperature, but at times it's not just reliability in terms of lifetime reliability, but it's also functional or operational reliability. So, and that could be just the steady state operating temperature device, but it could also be the temperature between different components of that electronics design. So in this example here, we have a kind of a system on chip where we have different parts of that die performing different functional jobs, and if there's a large temperature delta between these, it could affect the overall performance of that device. And this could be on one silicon die, or it could be spread amongst a number of chips. So I've been involved in projects where yes, we want to keep the temperature below a certain value, but we also want to keep certain devices within a certain operating range of each other to maximize our functional performance. We're also interested in predicting accurate junction temperatures, just simply to enable efficient designs. Because if we tend to underpredict component temperature, and so early in design process we're doing our thermal analysis and we're not predicting any issues, that would cause us to kind of maybe under design the thermal, whatever heat sink that we had to integrate, we would under design that. The opposite, if we tended to over predict temperatures, we may tend to over design. Maybe we use fans that aren't necessary, or bigger heat sinks that aren't actually going to be necessary. And we don't know that until we prototype and test. So ultimately, if we're having inaccurate early design predictions, it's going to ultimately lead to longer design cycles, because we're not matching what we thought, and we may have to redesign based on our new measured results. So the earlier we can get accurate temperature predictions, the less risk we have to over or under design, and it's ultimately going to lead to faster design cycles. So like I said, there's a number of approaches to modeling packages, and we're going to start with the simplest, which we'll just call simple, all the way to the most complex. So a simple is just really a bounding box of the package. So if whatever leads or solder balls or whatever, we're just representing that outline with a block with some effective thermal conductivity. And those conductivities, it's not hugely important what those values are. They just have to be, a reasonable value. I think any value between, I've seen, anywhere between like 10 and 20 watts per meter K is a reasonable value for this type of representation. And this would be used early in design process when you may not know what parts are being used, but you want to get an initial assessment of what risks you may have, or what how the thermal design might have to be driven, whether it be forced convection or yes, this part is going to need a heat sink. So you can learn things early on, even at a simple modeling level. Generally, what we say for the accuracy of the model is that it's going to be a rough estimate of the air and board temperature. So you can't expect to model a component as a block and get any reliable estimate of any kind of junction temperature of that device. It could be used for transients if you have this material block has a capacitance also. And that's going to vary largely based on what kind of package type it is. We have used this approach to model reflow ovens where you don't have this a huge transient analysis. You don't have the opportunity to model a lot of packages in detail, but you just want to capture kind of the transient bulk response. So you model a detailed IC package transient and then tune your effective properties to mimic what the detailed model would show you. So typically at this level, you're not doing a lot of transient analysis, so you don't have to worry about the heat capacitance and thermal conductivity, reasonable values somewhere around 10 to 20 watts per meter Kelvin. One step up from that, and perhaps maybe the most common modeling approach, is a 2-resistor model. And this is a common approach because you see a lot of data sheets for IC packages, and they may explicitly list what the junction to case and junction to board or junction to bottom thermal resistances are. And they're very easy to implement that way. Essentially, we have taken the same bounding box approach, but rather than having effective thermal conductivity, we've replaced that with a resistor network to capture the heat going from the top of the package and to the bottom. And the accuracy of these can vary widely depending on the heat transfer path in the model. So if you have a 2-resistor model with a big heat sink on top, getting the junction to case correct, if you have the correct value there, I think you're going to get reasonable estimates for the junction temperature. But we do say the accuracy of this model, good estimate of air and board temperature. It's not suitable for transient analysis because it's just a resistor network. It's not a resistor capacitor network. But I think these are probably the most commonly used. And one thing worth pointing out is you could develop a 2-resistor model either numerically or via measurement. So, and I'm going to talk a little bit about JEDEC standards when I can. JEDEC does not have a standard for 2-resistor model. JEDEC does define the measurements you would use to extract these resistances. So they have a standard for a top cold plate test, and that would allow us to generate what is this junction to case thermal resistance, where we're pulling out all the heat from the top of the package. We know what the heat is. We can measure the delta T, so we know what that thermal resistance is. We also there's also a standard for ring cold plate. So we can mount the board in this ring cold plate, draw all the heat through the bottom of the package into the board, and get the thermal resistance that way. So you can set up a physical measurement to do those, but you can also set up a numerical equivalent of that. You can easily build a top cold plate or ring cold plate model and extract what those thermal resistances are. So I just want to point out that these could be developed either through measurement or through simulation. The next approach would be, rather than to use 2 resistors, use multiple resistors. And the most common approach to this is what's called the Delphi model. And this is a JEDEC standard. So JEDEC has outlined the process of developing a multi-resistor network model for a IC component. And it essentially is, depending on the package type, you would impose, let's say, 40 sets of boundary conditions on this detailed component model and tune your resistances so that minimize the error between the detailed model and your resistor network model. And the hope is that when you use these 40 boundary conditions, that ultimately you're going to get quote unquote a boundary condition independent thermal network. That's the goal. Some of the difficulties with this approach is knowing what topology to use for the network. So you could see the you could start with, a junction is going to be connected to all the external nodes. You might have a top inner area, top outer area, sides, and then bottom inner and bottom outer. And then you use some optimization algorithm to determine what are the best resistances to use between those. So it could be a very accurate numerical representation. One of the challenges with this approach is if you ever try to look at this package definition and determine what package would be better or worse. So lots of times with data sheets, we'll look at so for a BGA package that we're going to put a heatsink on top of, we might look at the junction to case thermal resistance. And one package might have a value of 1 degree C per watt. Another package might have a value of 0.5 degrees C per watt. So you could just look at these two data sheets and determine that the one with 0.5 is going to require less of a thermal solution than the package that had a 1 degree C per watt. It's challenging to do that same sort of thing with a Delphi model because it's really just a numerical representation and not a mapping of the physical construction of the package. Anyway, it is a much more accurate package, and actually the standards states you should start with a validated detailed thermal model to use in development of this. While it may be possible to do this, extract this kind of resistor network from measurement, it's really not practical because, like I said, you're doing 40 sets of boundary conditions on this detail package. So it's really a numerical exercise. It's start with the detail package that's validated, however you determine it should be validated, and then exercise it with 40 sets of boundary conditions and extract what resistances minimize the error between the detailed versus the compact. So it's purely numerical process of developing this this compact model. It can be very accurate, but not for steady state. So there's no standardized approach for developing a Delphi model that has capacitances as well as resistances. And it should also be noted that there's no standard for creating a compact model with the Delphi approach that has more than one junction. So these multi-chip packages, there's no standardized approach for developing a compact model of a chip that has more than one die or more than one heated area inside that package. But it's second to the two-resistor model. This is probably the most common. What we see, I'll discuss now, in the thermal industry, electronics thermal, is that there's a lot of supply chain support. So vendors will provide compact thermal models, whether it's a Delphi, and here's a model that you can plug into your software, or just some values on a data sheet. These values are shared by vendors so that system integrators can build good predictive models for the entire system. So there's a lot of sharing of information. So it's important for there to be a process to share information from the vendor that gives the right information to the system integrator in terms of a model that will predict junction temperature, but not reveal anything else besides that. We don't want to reveal any kind of internal construction information of the detailed package. So these compact models kind of serve two purposes. One, to protect IP, and also to enable system integrators to build an accurate thermal model. Okay, so that's Delphi. Dan, I think we have our first poll question.
Excellent. Thank you, John. Let me go ahead and get that started. So this ties into what John's been discussing, and just to help us better understand how you receive IC package thermal models. So do your vendors provide IC package thermal models? And there's a couple options here, right? Typically, occasionally, rarely, never, or I've never inquired about getting models. Please just answer to the best of your knowledge. Again, it just helps in terms of framing and the additional material that John will be going over. So we'll give it just another few seconds before we continue on. All right. Appreciate everyone who was able to get us a quick response. So I'm going to go ahead and just share the poll. John, I'm not sure if you're able to see it, but just to read it out, 38% of our respondents shared that they've never inquired about getting models. That may be something you can touch on. The second largest category goes into occasionally, where their vendors do provide it. That's about 29%. And then typically rarely makes up another about 25% total. About 8% have never received IC package thermal models from their vendors. So just to give you an idea of how the audience skews. With that, it'd be great if you could maybe provide a comment, John, and then take it from there.
Great, thanks. No, I wasn't able to see the poll. Well, I would encourage you to ask your vendor. Vendors share information different ways. Some just post models directly on their website. So if you're a customer, you can log into their website and download models. Others, you may actually have to talk to your field representative and get a model that way. But just be aware that it's very common for this type of information to be shared between a IC vendor and what I would call a system integrator, people building the products that include those chips in their products. So it's very common in the industry, and I think it would be a question they would expect. They would know how to handle. They would be able to answer that question. So make sure you get models, especially for the critical components. The higher power components, the ones that are critical to the to your design. Why are you building this product? Maybe it has a GPU, CPU. So those are critical components to your design, and the performance of those components are ultimately going to affect the success of your product. So they would be able to share the right information with you so that you can build a reliable design. Okay. The next and final approach really is detailed, and we've broken it out into two kind of levels of detailed, a detailed 1 and a detailed 2. But at this level, we're modeling the physical geometry of all the components within the IC package. Detailed 1, see we have these on detailed 2 over here. We have explicit lead frame. We have all the leads coming out. Detailed 1 has merged those together and would, as a result, have some kind of effective material properties to represent this. And the reason you choose detailed 1 over detailed 2 is just the computational expense. This would require less mesh to resolve than this fully explicit one. But the difference between these two, you ultimately have to decide what's the purpose of why am I using the package. If it's only for temperature prediction, detailed 1 may give you the accuracy you need. But if you're really going to go downstream and do some, say, thermal mechanical stress analysis with the temperatures you're predicting from Simcenter Flotherm XT, you would want to do this fully explicit detailed 2, and then that could be mapped directly into Simcenter 3D for thermal mechanical stress analysis. But this detailed approach gives you the best opportunity to have the most accurate temperature predictions. And if you have the heat capacity of the individual elements, then it's going to give you the best transient prediction as well as steady state. Okay. So let's kind of look at all the different modeling methods and accuracy versus efficiency. So those are the methods we discussed. And in terms of accuracy, you know, the simple approach is going to have the lowest accuracy. If you do happen to get accurate temperature predictions at a junction, say once you prototype and measure, say, hey, that simple approach was dialed in on my measured junction temperature. Consider yourself lucky. That was just luck, not because this is a accurate predictive way of modeling. And generally, you know, our most accurate is going to be detailed 1 and detailed 2. Delphi, like I said, is really tuned to mimic the performance of these subject to those 40 boundary conditions. So its accuracy could be argued to be up in this range here. But generally, that's the trend. As you go from left to right of the methods we discussed, you're going to get more accuracy. But there's a penalty, really, in terms of time. So the quickest model build time and analysis time is definitely going to be from a simple approach where I just have a block. I'm going to give it a conductivity 10 and it has some heat dissipation. So you can build a model like that very quickly. 2 resistor could be quick also. You get the model from the vendor or just read a couple values from a data sheet. So that's very easy to do. Delphi, it could be argued that the time for Delphi could be right down here because the approach is to start with detailed models. So I have to first build a detailed model, so I have that time, and then I have the additional time of developing a compact or a network model representation of this detailed physical geometry. Delphi models can be also very time consuming to create because depending on the package, you have topology to determine, like junction to top inner, junction to top outer, the sides, maybe sides are treated differently, bottom inner, bottom outer. And then once the topology is chosen, then you run through your 40 boundary conditions and try and develop that model. If the accuracy isn't adequate for you, then you might have to try a different topology. Let's add some more resistors in this and determine what those values would be. Anyway, it's a iterative process to develop that multi-resistor network model that starts with this. So I would say Delphi could even be down here in terms of time. Computationally, once you get it in the model, it's very fast. These computationally are going to be very slow because I have to mesh everything. And so generally the mesh is going to be higher than with all these compact modeling approaches. If we look at the methods just with a table and summarize the accuracy and the benefits, point out a couple things here. With the detailed model, it's all internal dimensions and material properties are required. So if you're say a system integrator wanting to build a detailed model, explicit model, it might be difficult because chances are you're not going to be able to learn the internal structure from your vendor directly. So you don't have the information to use to build it. So there's kind of a bottleneck there, depending on where you are in the thermal design ecosystem. If you're an IC package vendor, then you know all that detail and you could easily create a detailed model like that. And I would say that most thermal designs are going to use a combination of all these approaches. So while I said this simple block is going to be used early in the design process, that doesn't mean that you're not using that approach also in a later design process, because typically you're going to choose a handful of what I'll call critical ICs, temperatures, parts that exhibited close to out of spec temperatures. Then you're going to want it. That indicates let me model that in more detail so I can get a very accurate prediction here, because I don't want to run the risk of over designing my thermal design because I am not accurately predicting temperatures. So use the block approach to map where you may have issues, and then you could choose to augment your design with more detailed approaches in those areas. But chances are most designs are going to use a combination of all of these. I did want to point out one other methodology that we've been working on the last couple of years, which is called the fantastic reduced order modeling approach. And this is you could think of it as approach to dynamic compact thermal modeling. So it's suitable for transients. It's an extension of this fantastic method pioneered by Professor Lorenzo Codicasa, where FANTASTIC is an acronym for Fast Novel Thermal Analysis Simulation Tool for Integrated Circuits. And it differs right now from, say, the typical compact thermal model, because the compact thermal modeling approaches that we have in industry are really intended for supply chain support, where vendor can supply a model to their customer. And it's just really to enhance our predictions inside our thermal analysis software like Simcenter Flotherm XT, where this reduced order modeling approach currently benefits, say, parallel design processes. Let's take all our model information from our 3D simulation model and create a reduced order model of that so that we can facilitate, say, electrothermal design or maybe a system level design. So I just have one slide to talk about this. This is a topic that to talk about in more detail, but I just want to introduce you to it. But you would start in these products and you have once you've built the model, export it as a thermal net list, which would be valid for that environment that was being modeled inside the software, or for a BCI-ROM approach where any thermal environment is suitable. So you specify the range that you want this ROM to be accurate for. And as part of the development process, you specify the required accuracy you want for that model. So you're guaranteed to have that accuracy for that model. And one of the nice things about this, like I said, it's transient, but it's also for any number of power sources. So if you had a stack package or just like a multi-chip module with laterally placed dies or different active areas on one chip, it's all supported with this one methodology. And once you've built a model and decided to go down this route, you have a number of ways that you can export that information. FMU, which is a standardized approach for sharing this type of information for like system level analysis tools, or VHDL, which would be useful for electrothermal analysis, or simply the matrices. So just the data that was extracted so that you can solve those matrices to predict the temperature response given a power profile. So this is a new approach that can handle any kind of package in terms of multiple junctions and is transient capable. That's where it really shines, is for transient analysis, because there really is no useful approach that's generally useful in industry today. So just wanted to kind of highlight that to you, that this technology is available. Oh, we have another poll question, Dan.
Excellent. I'm going to get that set up. And I think what you shared with the reduced order modeling piece, quite fascinating, John. And I'm curious if there's going to be more questions or follow-ups from that. But for those that are attending and paying attention, as you have more questions or if you'd like to explore that a little further in terms of the research, please do let us know. So you should be seeing the poll question: is transient temperature response a consideration in your thermal design? Love to hear from you on this. So typically, occasionally, rarely, or never. And again, don't get too lost between typically or occasionally. Like, please let us know what you're seeing. And if you have comments about, in which cases you'll see it, if it's occasional or typical, feel free to share those with us as well. I think it'll provide more insight. So we'll give it another few seconds. But John, did you have a point you wanted to add?
Yeah, I just want to say that, historically, when I first started in this industry, almost exclusively all thermal design was steady state. And maybe that's because, computers were slower, whatever reason. It just happened to usually always be steady state. And people lots of times design to, say, a thermal design power. Here's a chip. Here's the power that I should design to from the data sheet. But I see a trend over the last few years where more and more thermal design is based on either, say, use case, and a lot of it is because electronics are in everything now. With our smartphones and IoT, electronics are so much closer to human contact that there are more considerations. We have multiple environments that our devices operate in. We picking them up and holding them can, if they're too hot, if somebody thinks they're hot, that could affect the success of this product in the marketplace. So understanding the dynamic response when it comes to temperature of our end product is becoming more and more important for thermal design.
No, that's a great added tidbit there, John. And I think we see that reflected in the responses we got as well, where majority of respondents will see it in some form if we're looking at, transient temperature response, with a small handful, as in about 9% saying they've never seen it. So I think this lines up with how you've seen that shift in industry as we start seeing electronics and everything. So with that, I'll pass it back to you.
Great, thanks. Okay, so how do we go about creating these IC package thermal models? What are the challenges in generating a detailed thermal model? I've kind of alluded to them earlier, but where do you get the CAD geometry and material properties? So if you're a IC company, you might have a better opportunity of getting that information, but it may not really actually be in the format that you want, like a 3D solid model. So you may have to spend some time actually building up the CAD geometry. And where do you get the material properties? I don't know if you spent much time looking at material data sheets, and I haven't for a while, but in my experience, you might be able to get a thermal conductivity, but you really get no indication of what the heat capacity of that material is. So you end up making some engineering estimates on a lot of things just to build up a detailed model. So there's barriers in collecting information and building 3D models, which may not be your area of expertise in building 3D models. There's also the concern of matching the detailed modeling approach to the way you're going to model the PCB. And I'll talk a little bit about modeling PCBs today, but that will be a focus for next week, the next session. But really, when you model a detailed IC package, you really want to match that with a detailed representation of the board, at least in that area. So how do you match that? And what are the challenges in generating a compact thermal model? What topology should you use? Like if you go the Delphi approach, you could spin your wheels a long time determining what is the best topology to use. What boundary conditions to validate against. So different with the Delphi standard, depending on the package style, there's different recommended boundary conditions to correlate your model to. And if you did want this to be transient suitable, how do you incorporate the thermal capacitances for transient analysis? So there's a lot of work potentially in building these compact models or detailed models. And if you get anything from your vendor, it's going to save you a huge amount of time and improve the accuracy of your models. One thing we offer to assist in the creation of detailed and compact thermal models, and we've had this spinner product of ours for some time, is Simcenter Flotherm Pack, which is a web-based subscription tool. But at a high level, you log in and you get presented with a mini package styles you can start with. And then you pick the package style you're wanting to build a package for. And historically, there's been two types of customers for this. One IC vendor who knows all the detailed information, and two, the system integrator, which has a need to build a more accurate predictive model, but has very limited data. They have the data sheet, which may have a mechanical drawing and give them some dimensions, but certainly not all the information that is needed. So this kind of interface supports both, where you either know all the information or you have very limited information, because once you've chosen the package style, it walks you through a wizard where you can populate the answers with your known data, or have Flotherm Pack fill in those blanks for you. So at the end, you have a reasonably accurate predictive model here based on, common values used in industry. Once you have that, then you can either download the detailed model and run it in Simcenter Flotherm XT, or you click a button to generate a 2-resistor or Delphi compact thermal model. So all the technology or decision making to develop a Delphi model is integrated in this tool. So you just click a button, say I want the Delphi model, and then it emails you once it's complete. Might take 5 or 10 minutes for it to develop the Delphi model. It sends you an email, and then you go download the part. So this really streamlined the kind of compact thermal model development process, where you fill in the data sheet with assistance from the wizard and can quickly get a thermal model, either detailed or compact. The other method is relatively new, where we have this Flotherm Package Creator, which I'm going to talk about, but I'm going to do it through kind of a worked example within Simcenter Flotherm XT, kind of look at the workflow that you would use. Typically, when you're doing a thermal model in Simcenter Flotherm XT, you're going to start with CAD. You have some CAD data, and you also have ECAD. So say a routed board in Expedition, you read that board into Simcenter Flotherm XT EDA Bridge, you bring that into Simcenter Flotherm XT where your CAD model is, and then you analyze it and get the temperatures that you're looking for. Okay. So to model the board, we've read in the design, here we've identified 5 components that are deemed critical, that we want to model in more detail. And since we're going to model these little SOP packages in more detail, and we notice there's copper in this area, that's going to affect the way we want to model the PCB. We want to not smear this copper all across the board. We really want this discrete area where we have a lot of copper and have that represented in our board. So we're going to swap those components with a detailed approach. And after we transfer to Simcenter Flotherm XT, we have the explicit copper represented and a detailed representation of that package. Okay. So how to create the package model. So this, I want to introduce you to Simcenter Flotherm Package Creator. There's 3 main areas. The package manager, these are packages you've already created. The wizard launch page, so very similar to Simcenter Flotherm Pack, where you start with a wizard based on the package type. And then the package detail, once you've worked through the wizard, you have the opportunity to modify values, make some thermal modeling choices. So from the Create New Package screen, you can refine the search for certain package types and then make your choice. In this case, it was a SOP that we wanted to use. And then we launched the wizard. Give it a name, standard outline, and then we have all these parts that we can use directly or start with. Pick the one that makes the most sense based on the package we're trying to model. So this information, we're going to read off the data sheet. Give it a power. And then the die size is automatically populated. But again, we can change those values here or in the property sheet once we've worked through the wizard. It asks us this up front because, the die size, very important in terms of the overall thermal performance of the package. And whether or not this particular package has an exposed pad. Lead frame material, once you've worked through the wizard, you see all the package information. The areas of the interface are, we have all the, what we're calling smart parts here, all the different sub-assemblies that would be used to build up this part, and each one with its associated property sheet. And then over here, just a graphical display of that part. So for this SOP package, we have a tie bar, the die attach, the die assembly, the lead frame, bond wires, the encapsulant, and thermal land if we have one of those, and overall. We can make changes. We can see it update in the user interface window there. It supports full undo and redo. And it highlights conflicts. So if you've put in information that doesn't allow it to build a physical geometry, it's going to flag that to you. Once you've built a package, you can export the package into this XT XML-A format. This is a format for Simcenter Flotherm XT, a human readable XML file that defines the construction of that package. So it's a shareable package for you to bring into Simcenter Flotherm XT or share with colleague or share with a customer. You can also save it in here directly, so it's part of your interface in Package Creator. Okay, and you could also load. Somebody provides you a model, you can load it in here, make changes to it, and then save it out again. Take a quick look at if we did a BGA. So we're also using a BGA package in our model. Some of the things to highlight, we walk through the wizard. It's probably kind of difficult to see here, but the package size, number of solder balls, and the die size, some of the major choices there. Once we work through the wizard, we see all the solder balls are here, but we can say it has a center depopulation here, but it has central balls. We could do it that way. And then some examples of some modeling choices would be if we want to not model each individual solder ball, but model those areas with an effective conductivity, we can do that, and it can calculate the material properties just based on this quick setting. Another area we may choose to make some modeling choices here are bond wires, whether we model the bond wires at all, or if we model them in a compact way, so it's going to be less meshing. Could be our bond wires aren't critical for our temperature prediction, but we want to include them, so we may choose this option right here. Okay. So create a library. Once I've built up the models and saved them to disk, I can, inside Simcenter Flotherm XT, import those assemblies. There I see the part in Simcenter Flotherm XT, and then I can just drag it over to my library. Once it's in my library, then I can use it in the EDA bridge to swap components. So we have our model, we have our CAD. We just have the CAD. We haven't identified this as a Simcenter Flotherm XT model. The way you do that, just quickly, is you walk through a wizard to help set up the model. You have a choice. Do you want to start with the empty assembly? In this case, we're going to start with the active assembly. We have a CAD assembly opened. We're going to build a Flotherm XT model based on this assembly. We've walked through the wizard. At the end, we have our Simcenter Flotherm XT model. The next step would be to launch the EDA bridge. We did that. We imported our routed board. We see it here. The next step would be to swap the parts in. You can see that I've opened up the parts library here, and we can see the parts that I created in Package Creator. Those are the 5 components that we want to swap out. You can swap them out using package name or part number. We're going to swap just one-offs. So we'll select a package, say replace this part with the one I have selected. So I select, for example, this BGA, select the one that I want to be swapped in from my library, and just use the replace selected. And now it's this explicitly detailed package model placed correctly on my board that I read in from the whatever tool routed it. Okay. So I've done all that, swapped the 5 parts, transferred it to Simcenter Flotherm XT. I'm going to show you I'm going to position the board. I just have these 2 edges selected, and I'm going to make them concentric. Now it's located properly, and then I can mesh it and solve it. So I've added a heat sink, and we'll just take a quick look at some of the results. Point out one very useful feature for Simcenter Flotherm XT is this ability to color components by their with respect to their temperature limit, whether it's junction or case. So you can easily flag which components are critical. Like I said, next week's session is going to talk about EDA bridge interface in more detail. This is just kind of a quick workflow example. I can also get that information out in a table where I can see the temperature limits and what the actual temperature was, and the cells are colored by how close they are to their temperature limit. Okay. So once you've done that, you could use Flotherm XT to look at the efficiency of heat sinks and vents, or even touch temperature. So a lot of thermal designs, like I was saying, electronics are everywhere, very close to consumers, where it can actually touch them. So many times the limiting factor isn't the actual junction temperature of the IC chip, but it's actually the external enclosure temperature. So for many thermal designs, the external touch temperature is the driving parameter, and that's why we're highlighting it here. So that was just a quick workflow example where we have kind of two methods of developing detail packages. One, Simcenter Flotherm Pack, the other, the Package Creator. Package Creator is going to allow you to create detailed models that would be suitable for, say, downstream thermomechanical stress analysis. The detailed models in Simcenter Flotherm Pack would be, I think, representative of a detailed approach where you're not going to want to model the explicit geometry, but a detailed, kind of quasi-detailed approach where I can get a good predictive model without modeling, say, the bond wires in physical detail. For compact model development right now, Flotherm Pack is what we offer for developing the Delphi models or two resistor models. And then, of course, we have the BCI-ROM approach that isn't used within the CFD software, but the software is used to develop them for parallel workflows. Now, so we have a lot of opportunities to build detailed models, but just because we added all the explicit geometry and attached materials to them doesn't mean they're accurate. They have the best opportunity to be accurate, but the only way that we know they're accurate is if we can validate them against a measurement. So let's look at a legacy approach of how you might validate a compact, or not a compact, but validate a detailed model. So they all start with measurement. You need something to validate against. Many times the measurement is a steady state temperatures at discrete points, where that's a on-die sensor or a thermocouple on the outside. There's some kind of discrete areas that we're measuring a temperature at a given power, okay? The next step would be, we build a model like we would before with our best estimates for material properties and physical construction. And then we analyze that, we iterate, we guess, and inspect, and simulate. So we look at results, we change values, we look at results again, and we go round and round until, honestly, what happens is you run out of time. And many times you rationalize that what I've done is good enough. I mean, it's better than what you had, but is it accurate for everything? No, it's not, but it's better than what I had, and we hope it's good enough. That's kind of the legacy approach. It's very limited by time and engineering expertise. How well are you, how experienced are you at trying to modify a model and tune it to measurement results? So that's one of the issues. Poll question, Dan.
Great. Sorry, I realized I was talking on mute. I'm sure we've all seen that happen these days. All right. So you should be seeing it on your screen. This is our last poll question, but please do continue to answer or ask questions as you have them. In this case, you can select multiple answers here. We received that feedback from you in the last session that you'd like that option. So what is the biggest barrier to model calibration? And please feel free to add some more as needed. Time, expertise, suitable measurement results, other, or I don't calibrate models. And again, feel free to send us a note if you'd like to share more specifics around if it's other, or if there's any clarification that you need. Yeah, I think personally very curious about this one, as I've heard variations of answers when it comes to this thought process, John. So let's see what people are saying. So from our audience, in terms of the biggest barrier, quite a few people, suitable measurement results. Okay, that's one that we see quite a bit. Almost half the respondents see that in some capacity or another. And then time and expertise also being a big factor. For those that put other, I'd be curious in learning a bit more. Please do feel free to send us a short comment if you'd like to share, as that'll just help us in helping companies overcome this barrier. And of course, as expected, a certain number don't do any calibration. So, John, would love to hear your thoughts on how this relates to what you're seeing and have been seeing in your 20 years of experience. I'll give you back the screen, and if you want to share a comment and move forward, let's do that.
Okay, yeah. I mean, in my experience, it's it's all over the map, really, with kind of the ways to answer that poll question. There are some customers that really have a great process of validating their thermal models, and it depends on, say, what level, where you are in the thermal design kind of ecosystem. Really, if you're IC package vendor, it might be easier for you to calibrate a model, and system integrators more difficult, because you're building models based on a lot of data that's been shared to you. I think if I had to say, I think what is most common is I think a lot of people, you go through one design process, you build your prototype, and you measure the results from that, and you look back at what your thermal analysis said, was telling you, and you might leverage the information you learned from that to build a better design the next time around. So a better model of the next design. So you start to learn where, say, your assumptions are affecting your accuracy, and build that into the next product you develop, rather than a kind of dialed in, kind of repeatable, scalable calibration process. Just kind of from learned experience, build better models next time around. That's probably, if I had to say the bulk of what I see, I would say it falls into that category. I do want to point out, said a lot of, in my experience, a lot of the measurements are kind of steady state. And if you're just trying to calibrate to point values, there's a risk of getting the right answer for the wrong reason, because these pictures here don't maybe illustrate it that well, but you could have two materials of different sizes and materials, and they could both provide the same thermal resistance. So in essence, if this stack up here was encapsulated and you didn't know what was inside there, the stack up could be different. And to be honest, these are going to give significantly probably different transient responses. So it's much easier to calibrate to steady state temperatures, but a much higher risk of getting the right answer for the wrong reason. Okay. Now, if all you're designing to is steady state temperatures, this may be okay. But if you're trying to develop a model that's accurate for dynamic temperature response, then you really need to calibrate to a transient temperature measurement. And that brings us to the Tristram measurement. Our calibration process in Simcenter Flotherm, Simcenter Flotherm XT, and Simcenter FlowFD is based on the Tristram measurement. And just to give you a high level overview of that, this would be the Tristram right here. So it's a physical measurement hardware where we don't measure with, say, a thermocouple. It's an electrical test that I'm going to try and briefly highlight here. So we connect to the device that's mounted on this heatsink with wires, and we power that device. It's a standardized approach to JEDEC 51-1 and get electrical test method. But once you've got it set up, the process would be either to provide a low power until you reach steady state, and then step that power up to a new value until you reach steady state again. Whoops. And then during this step process, you're measuring temperature of this device. So I'm skipping a lot of detail here, but at the end of the measurement, you want to get this temperature versus time between two power states and two steady state temperature responses, okay? And we can learn a lot of information from this temperature versus time response because the software that accompanies the hardware develops what we call a structure function. And a structure function is a plot of, on the vertical here, we have the thermal capacitance, on the horizontal thermal resistance. And on the lower left-hand side, that's where the heat source is, so the junction. And as we move to the right, that's the heat sink where we have infinite thermal capacitance, where the heat sink is the ambient air or a cold plate or a heat sink in this example. And this is the thermal structure of the heat transfer path. And if we just take a look at a simple package here, this area would represent the die attach, die flag, mount, and the cold plate. So you can't tell this information by looking at this one plot, but I just want to highlight to you that this structure function is actually kind of a map of the entire heat transfer path from source to sink. And this is what we're going to use to calibrate our thermal model. We would build a Simcenter Flotherm XT model of this measurement setup where we have all the detail of the package mounted on a cold plate and exercise it to tune it to match this curve right here. Okay. So the automated calibration method would be to have your model and then just do a design of experiments and optimization with this calibration interface to minimize the error between that structure function, which is the transient response, versus your detailed prediction of that transient response. So really, it reduces the calibration task to specifying ranges of the parameters not known with certainty. So you kind of define your design space and then tell it how many designs to do, and then it will minimize the error between the measurement results and your predictive model. And we'll show you an example here. But so the process becomes, you start with the measurement. The Tristor measurement is a great measurement to calibrate to because, like I said, it's transient and it gives you the thermal structure between the heat source and the heat sink instead of point values along the way. When you're setting up the model, you're setting up the design space and use the auto calibration setup to explore that design space and optimize the parameters to match the measurement results. So at the end, you have a fully calibrated model. It will tell you the accuracy of that predictive model, how well it was able to match that structure function. So at the end, you have a process that performs it and gives you the result in terms of how accurate that prediction is. So the process would be, said we start with the Simcenter Tristor measurement where we have IGBT. The software with the Tristor calculates this structure function here, and then we can export that to a file that can be read into any one of our softwares that I mentioned before. We'll be looking at Simcenter Flotherm. That's the example I've set up. But like I said, we want to build a simulation model that matches the test setup. And it's a transient measurement. So we want to set up a transient simulation. And I'm just showing this dialog here to indicate that we want to start with very small time steps. If we want to, say, calibrate our die attached material, that is very early in that thermal path. And to capture that accurately, we need to start with some very small time steps because that change happens very soon after our transient starts. So we start at, microseconds and all the way up till we reach the steady state here. And each kind of decade of time, you would want, say, 10 to 15 time steps across that to accurately kind of represent the structure function and the kind of the measurement fidelity. So that just gives you an indication of this is a transient correlation and we need to have a transient analysis. So we want to quantify these areas that we're uncertain about. Some of the areas that we typically see that are uncertainties are the active area of the die. So when we build thermal models, we generally just have the heat dissipation across the entire footprint of the die. That isn't accurate, and tuning that area can have a significant effect on the transient response of that chip. So active area size is one. The other one is material properties, where it's thermal conductivity, heat capacity. But another really important one, and I think something that is never captured in thermal models, is the contact thermal resistance. So when we build a thermal model of this, we have one material adjacent to another material, and just by default assume they're perfectly connected. Even with the thermal interface material, we just, whatever we read off the data sheet, that's what we use. But there could be a contact thermal resistance there that we're not capturing. So just looking at if we perturb those contact thermal resistance a little bit, does that improve our accuracy? So those things we're going to that we typically look at. So this would be Simcenter Flotherm. We have set up our design space, and this is our calibration dialog here. In this example, I've broken up the calibration process to two phases. The first phase is that area around the die, and then the second phase will be further along in the thermal path. But I have a short video we'll talk through here. This is, I'm setting up my design space where I'm going to modify the active area and some conductivities. I import the twistor measurement. We read in the structure function here, the blue line is from the measurement. I can do a setup check to verify that my Flotherm model is the same as the twistor measurement. I see the power, the duration, and the initial temperatures are the same. So I'm good there. The next step would be to identify what temperature within the model do I want to use to correlate against. Once I've done that, it can calculate a structure function from the model, the red line, and we see there's quite a disparity between the red line and the blue line. I have my design space here. At a minimum, I'm going to do 5 designs for each input. So that gives me 15 designs. And I'm going to adjust the calibration extent. So when I'm calculating the error of the response, just focus on this area, because that's the area that's going to be affected by my inputs. So I did all these designs. If I just switch to the lowest cost, I could see that I'm much better representing that response and around that die attach area with just 15 designs. We also get other things, like I said, is does a design of experiments here. Sorry, let's just look at the active area. We see it's a little bit smaller than the full footprint of the die. But like I said, we do a design of experiments. We can see the response surface. So we can see how the inputs we decided to look at, how that's affecting our outputs. Once I've done the calibration of this first phase, I save it out, and I could do the second phase of my calibration further down the heat transfer path. So rather than show a demo video of that, I just have the result here. In this second phase, I'm looking at the ceramic and solder layer contact resistances. So I'm not modifying any of the material parameters I've built into the model, just contact resistances on either side of those interfaces. And if we look at the lowest cost, the best design from this second phase, I can see I'm very well matched to that measurement result. So if we compare the uncalibrated result to the calibrated, we see we get a much better match, like I said. And the ultimate final values here, this is the active area I changed. So I just changed it a little bit from the full footprint of the die that I had initially. And for the contact resistances here, these are very small values, in my opinion. So I just modified those values a little bit, but I was able to much more accurately represent the physical measurement by just modifying these values a little bit. And this process, if you had to do it manually, it would be so time consuming that it really wouldn't be practical in your typical design process. And we may not, I didn't point it out, during the video, but as part of that calibration process, it reports the error, how well it was able to match along this curve. And this was greater than 99%. Like I said, I didn't do that many designs. You could do more designs and maybe get better matching, but this is an example. So with 15 designs and a numerical prediction of where the best would be off that, I got a good, great correlation, really. So in summary, junction temperature is a good lead indicator for reliability. I have recently, over the last couple of years, remind myself that and discuss it anytime I can at the beginning of a presentation, because our thermal design process, we always look at junction temperature. Why is junction temperature the driver? It's because it's a good lead indicator for reliability of that product. Simcenter Package Creator and Flowtherm Pack create IC package models from true resistor to explicit detailed. So that's what we offer to enable you to create detailed and compact thermal models of IC packages. And I briefly touched on BCI ROM, which is enabling technology currently for parallel design flows. And we looked at the automatic calibration process and Simcenter Tristor, how its measurement is really well suited for this type of calibration methodology. And once you calibrate against that, it's good for any kind of steady state or transient profile you might put on that device in any kind of system. Okay, so that briefly, that's what we discussed. But I'd be happy to take any questions and try and answer them. And I did want to point out that we're offering a complimentary Simcenter Flotherm XT evaluation at this link, which I think will be put in the chat box. But you give Simcenter Flotherm XT a try and look at some of the things we discussed today.
Excellent. Thank you so much for that. I think you covered a lot in a very short amount of time. We have had questions trickling in, a lot of which we've been answering throughout. A couple that may be good to get your input on as well, John. We'll start with this one, since towards the end of your presentation you talked more about calibration. Can you speak as to why you broke the calibration process into two phases?
Yeah, sure. Yeah, partly I did that because I think that I wanted to try and illustrate how the modifying parameters around the die area affect the curve in that area. So you could kind of start to see how this structure function is actually a structure of the thermal path. That may have not come across very well because we went through it quickly. So I wanted to highlight that. But two, because I'm only doing, say in that first part, I did 15 designs, I wanted to just limit the calibration extent, so just that area around there. So I'm able to do fewer designs in a focused area and get better results. I could have done the entire curve with more designs and done it all in one step, but I choose to do it in 2 steps with reduced number of designs in a focused area.
Great. I think that provides a lot of clarity. Before I get to the next question, again, just a reminder, we have put a complimentary link to an evaluation of the Simcenter Flotherm XT tool. You should see that in the chat window as well for Mario to make it easier for you to copy paste into your browser. Another question for you that I'll jump into, John, and this relates to one of the earlier poll questions on vendor values. So can you speak a little bit as to what sort of error would you expect from vendor values to calibrated models? Or if the answer is more along, hey, it depends, maybe you can talk about how you deal with errors in relation to vendor values, or how that links up with calibration or calibrated models.
That's a really good question, and kind of probably difficult to answer. Without knowing what individual vendors are doing. I think that when you're looking at accuracy for a model provided, you have to, and assuming those are some kind of compact thermal model, there's inherent accuracy issues with those compact thermal models. A Delphi model, you know, is supposedly boundary condition independent. That's the goal of the whole approach. You start with a validated model. I think it's up to the vendor to decide what it means, what is a validated model to them, you know, and without discussing that directly with them, but because the network representation is directly related to how accurate that original detailed model was. But the Delphi approach is, and part of the Delphi standard, to be honest, is provide the network, also provide the predictive accuracy. So how accurately, and usually they're like less than 1% difference between the detailed and the compact model. So they're generally very capable of matching the detailed model, but how well that detailed model matches the results and what measurement results were they calibrating to, you know, to me, it should be calibrated against a Tristor measurement because that's a full dynamic response. But I don't believe every vendor is doing that. So that's probably part of the where some of the error could be introduced. But once you go to 2 resistor, you know, the predictive accuracy of that approach is you know, 20-30% in that range to begin with.
Very insightful, thank you. And I do believe we added more details in the question feature for whoever asked that. So please let us know if you need further clarification. I have 2 more for you, John, and maybe that's where we'll wrap up unless another question comes in that we can address. But we'll start with this one over here. Give me 1 second. Yes, so let's say I have a BGA package having 3D dies stack up. How do you model this type of package quickly?
The way I would model that package quickly is use our package creator, and then once you've read that into Simcenter Flotherm XT, you know, maybe I could take that die subassembly and pattern it, or replicate that part. So once I get the package kind of structure in there, each individual element is a CAD model that has the thermal properties associated with it, and I can modify that within the tool, Simcenter Flotherm XT directly, get the actual package configuration I have, and then drop that into my library for swapping in an EDA bridge or bringing into another model.
Very helpful. And while we're on the topic of, let's say, speedy modeling, let's talk about the examples that you showed, John. How long did it take for you to create the detailed model geometry in those examples? Could you speak to that?
Oh yeah, it's very quick. You know, in Package Creator, you would step through the wizard, and assuming you're not interrogating all the inputs, it's as fast as you can click through the software. It's very quick.
Wonderful, appreciate it. And again, I know we're answering a couple more questions as they're coming in, but we'll leave it at that. Just to wrap up the series, please do let us know if you need more questions answered, or if we missed any, we will circle back on those by email. Again, we have a link. This is ready-made, complimentary, just for those that registered and signed up for this webinar series. So please take a look. If you want to get your hands on the tool, that's the link there for you. So, and just wrapping up what we're showing you all today, I'm just going to go ahead and share that. If you could just move to the next slide, John.
Okay.
Yep. As you can see, we covered the fundamentals of electronics cooling last week. John did a fantastic job today in showing us a workflow demonstration of using Package Creator to generate thermal IC package models. We talked a little about calibration as well, and fielded quite a few questions there. At this point, again, the evaluation is available, complimentary for those that like to try it out. Next week, we will be covering PCB level thermal analysis. It should be a very exciting session there. So we'll go from CAD to electronics cooling within Flotherm XT, and also introduce the EDA bridge. In the final session, we'll be wrapping up thermal testing and validation. So as you saw with this session, we will continue to share materials. You can expect the recording later this week. And if there's any questions we missed, Mario will be answering those as well in the coming days. So we appreciate that. John, if you could just skip to the next slide. Yep, we will have additional webinars, so please go ahead and check those out. This is one of the series we're conducting. We will have additional ones that are either going on right now or coming up in the future, so you can check those out at that link. And John, I believe that wraps us up, or almost wraps us up, if you could just move to the next one. Wonderful.
Yeah.
There's John's email if you'd like to check that out. Again, thank you so much. I think we covered a great deal today. Any other questions, do let us know. Watch out for the follow-up material, and we look forward to discussing with you in next week's session. Wish you all have a great week ahead. Thanks again, John. Fantastic job.
Thank you.
Bye now.